Hello, my name is Isaac and I'm a tutor at CWI. Today I'm going to be running through a practice problem from Physics 112. It's from practice exam number 2 and I'll be looking at problem number 7. So problem 7 states that a straight wire of length 50 centimeters carries a current of 40 amps and a uniform magnetic field of 80 millitesla. The force on the wire is 1 Newton, so now we need to determine the angle between the wire and the magnetic field. So what we know is we have a length of straight wire, and it's of known length. That length is equal to 50 centimeters, which of course is 0.5 meters. And there's a current going through it. The current is massive, it's 40 amps. It's a very dangerous amount of current. And so let's draw the current going this way. Current I equals 40 amps. Alright, and there's a uniform magnetic field permeating the whole region of 80 millitesla. So I'm going to draw a magnetic field, and just imagine that these lines extend throughout the whole problem. But I'm just going to draw those two lines to represent the B field, which is equal to 80 millitesla, so 80 times 10 to the minus 3 Tesla. And what we're really looking for is the angle between the wire and the magnetic field, given that the force caused by the magnetic field on the wire is 1 Newton. So we know that there's some force caused by the magnetic field on the wire of 1 Newton. And now we need to figure out what equation to use. And I would just like to start off using part of the Lorentz force equation, the magnetic part, because there's no electric field here that we're dealing with. There is one in the wire, but we're ignoring that. So the Lorentz force claims that force equals QV, so charge times velocity, crossing the velocity with B. And of course, if we're looking at velocity, one way to think about this is for a particle. It's for a one charge particle. Well, the thing is we're dealing with a whole bunch of charges in the wire. And so how are we going to take care of that and rewrite the equation? Well, velocity can in fact be written as displacement per unit time. Let's go ahead and say that the displacement is the length of the wire. So velocity can be written as the length of the wire per unit time. So now that we have that, we can fill in the rest of our equation. And that's equal to our force. Cleverly, we're going to go ahead and take time out of, because time is a scalar, it doesn't need to be part of the cross product in order to maintain the correct direction. So we can pull out time and put it underneath Q. And then we can say L cross B equals force. Now, charge per time is a flow of charge, and we call that current. So we can rewrite Q over T as I, or the current in the wire. I times L cross B is equal to the force on this wire due to the magnetic field. Now, it's important in these problems that your length vector points in the same direction as your current. Now, current isn't a vector, it's a scalar, but the length that current flows upon has to have a direction, otherwise we can't do L cross B. So we're going to say that this is the length vector direction, and of course this is the B vector direction, and we're looking for an angle between it, angle between L and B, theta. And that's what the cross product does, is we're going to take L cross B, and that's going to give us our direction of the force using the right hand rule. So the force here is coming out of the board. Now we could indicate that with it's coming out of the board, so we can do a circle with a dot in it, and that's going to be our force of 1 Newton coming out of the board. Alright, so now that we know that, we also know that L cross B, instead of dealing with it as a vector, we can find L cross B by saying L times B times sine theta. So the magnitude of L times the magnitude of B times sine of the angle between them, all multiplied by this current out front, and that's going to equal force. So now we have a nice equation. This one might be a good equation to write down on your cheat sheet of equations. That way you don't have to derive it every time. And now we can go ahead and plug in our values. So we know that the force is equal to 1 Newton. So we have 1 on this side. The current is going to be 40 amps. So we have 40 amps. The length of the wire given is 0.5 meters. It was given as 50 centimeters, but we converted that. Times the B field strength in Tesla, which is 80 times 10 to the minus 3. Why not just convert this right now and move the decimal 3 places to the left? So now we just have a B field of strength 0.08 Tesla, and all of that is going to be multiplied by sine theta. So now we need to solve for theta. So let's go ahead and multiply all these numbers together. The 40 amps times the 0.5 meters times the 0.08 Tesla strength field. And so then at that point I've reduced this to 1 equals 1.6 times sine theta. We're going to go ahead and divide both sides by 1.6. And 1 divided by 1.6 is 0.625. 0.625 equals sine theta. And we can take the arc trig function for sine on both sides to tell us that theta equals the arc sine of 0.625. You may also see this written as sine minus 1 of 0.625. You'll probably see that more likely in your book. I prefer to use arc sine. So now that we know that, we want to make sure that our calculator is in either degree or radian mode, depending on what the answer is to be given in. I'm sticking with degrees on this one. So I'm going to take the arc sine of 0.625, and I've given an angle of approximately 38.7 degrees. And so that is the angle that this wire must make with the B field in order to give that 1 Newton force that we measured. In this case, it's kind of a funny problem because, of course, you can't have a current carrying wire that's not connected to itself in a circuit. But for the sake of theoretics, we're just going to pretend like we can have a current of 40 amps flowing through an open circuit. So I hope this video was helpful to you. Please leave comments on problems that you'd like me to solve. Thanks, and have a nice day.